According to Einstein's theory of relativity, if it were possible to send information faster than the speed of light, then it would also be possible to send information backwards in time. However, according to quantum mechanics, instantaneous messages faster than the speed of light appear to occur when we have quantum entanglement. Some interpretations of quantum mechanics state that information is, in fact, being sent backwards in time, but that time-traveling paradoxes are avoided because this information consists only of random quantum outcomes, which we have no control over. Hence, it is not possible to use this phenomenon to encode useful information, and it is therefore not possible to change past events which have already occurred. Some interpretations of quantum mechanics take an even more intriguing approach to time travel. An electron moving forward in time can be thought of as a positron moving backwards in time. The transactional interpretation of quantum mechanics states that it is not possible to send information faster than the speed of light, but explains quantum entanglement by saying that quantum wave functions travel both forwards and backwards in time. This interpretation states that it's the transaction between the wave functions traveling forward in time and the wave functions traveling backwards in time, which is responsible for what we think of as wave function collapse. The transactional interpretation of quantum mechanics does not take a position on whether or not the future is predetermined. The wave functions traveling backwards in time can be traveling to us from different possible futures, rather than just from a single future which is predetermined. Suppose we ignore quantum mechanics and just focus on Albert Einstein's general theory of relativity. Time travel to the past using general relativity alone is problematic, as we wouldn't know how to resolve time-traveling paradoxes, which involve trying to change past events which have already occurred. Nevertheless, there are some proposals about how Einstein's field equations of general relativity might potentially allow time travel to the past. One proposal was made by Gödel. This requires a rotating universe, with a negative cosmological constant to balance out the rotation and keep the size of the universe constant. Gödel found that if you followed a particular path in such a rotating universe, you could time travel to your own past. You would have to travel billions of light years to accomplish this, but it could be done in principle. Though, this technique can't be done in the universe we actually live in, since we do not live in the type of rotating universe that this proposal requires. Another proposal for time travel using general relativity involves the use of cosmic strings, not to be confused with string theory. Cosmic strings are topological defects in the fabric of space-time that theoretically could have been formed in the first few moments after the Big Bang, and would still continue to exist today. Cosmic strings would have a width that is far less than an atomic nucleus, but have a mass-energy density of about 10 million billion tons per centimeter. A cosmic string could make a closed loop or have an infinite length stretching across the universe. If we had two infinitely long cosmic strings moving very rapidly past each other, and we traveled in a carefully calculated figure 8 around them, we could time travel and emerge in the past. Time travel to the past could also be done by using a single cosmic string and a black hole. However, cosmic strings have not yet been observed to exist, and their existence is therefore entirely speculative. The last proposal we wish to consider for using general relativity for time travel to the past is wormholes. The theory of relativity states that it's not possible to travel through space faster than the speed of light. This has frustrated many science fiction authors who propose getting around this inconvenient fact with the use of wormholes. Wormholes are not known to exist. If they did exist, then keeping them open would require something with a negative energy density, which is also not known to exist. But if wormholes were to exist, then Einstein's general theory of relativity states that not only would it be possible to travel to a distant point in space, but it would also be possible to use wormholes to travel through time to the past. As stated at the beginning of this video, according to Einstein's theory of relativity, if it were possible to travel faster than the speed of light, then it would also be possible to travel backwards in time. This is one of the arguments for why wormholes cannot exist. Although time travel to the past using general relativity is problematic, time travel to the distant future is not controversial. We know this can be done using the presently understood laws of physics. If Adam travels at near the speed of light, then when he returns, only a few minutes will have passed for him, while many decades will have passed for Sarah. As an alternative method for time travel to the future, if Adam goes near a black hole, time will pass much slower for him than for Sarah. When Adam returns, he again will have aged far less than Sarah. By using either of these techniques, we can travel as arbitrarily far into the distant future as we wish, even to the time long after the heat death of the universe, when all the stars have been extinguished and life no longer exists. That is, no life with the exception of a few brave time-traveling explorers such as ourselves who chose to journey to this distant future. An explanation of these phenomena is available in the introductory video, Albert Einstein's Theory of Relativity. A detailed explanation of some of the other topics we have covered is available in the video, Quantum Physics, List of Philosophical Interpretations. Thank you to all the people supporting us on Patreon. Your support is very much appreciated.